Okay, can you please read the question from? Just ignore the magnetic flux density first because we didn't do it yet. We have to do that in the next chapter. Okay. So, okay, start from this one.
Electrons, each of mass m and charge q, are accelerated from rest in a vacuum through potential difference v, and derive an expression in terms of m, q, and v for the final speed of the electrons. Explain your working.
Okay. So we can say that so kinetic energy has a formula Ke is equals to half mv squared. Okay. So kinetic energy is equals to half mv squared, right? Right. And work done is basically force times distance. Okay. This is the concept. Or you can, okay, we have the potential difference. Okay. We can we can use two different things. Um, Electric field is equals to F over D, and electric field is equals, sorry, F over Q, and electric field is equals to V over D, right? So if we equate the two electric field concepts, so we'll end up getting F over Q is equals to V over D, okay? And then F times Q is basically the work done, okay? F times D is the work done, and V times Q is equal to work done, right? And we know that if the charged particle is moving, so the change in energy is basically the work done, or the work done will convert into the change in energy, right? So, okay, so we can say that work done is equals to change in kinetic energy, right? This is our explanation. Okay, and the work done is basically Q times V times Q, where V is the voltage, not the velocity. And change in kinetic energy, if we, okay, the charged particle is accelerated from the rest, so the initial velocity is going to be zero. So the change is equivalent to half mv squared, right? So you can make V the subject. So 2 times voltage times Q over m under root gives you the velocity. Is that clear? Okay, so please move on.
The accelerated electrons in B are injected at a point S into a region of uniform magnetic field of flux density B. So flux density.
Yeah, it's basically magnetic field.
Okay. The electrons move at right angles to the direction of the magnetic field. The path of the electrons is a circle of radius r. Show that the specific charge q upon m of the electrons is given by the expression q upon m is equals to 2v over b square r square. Explain your work.
Okay. So we can see that the magnetic force is basically causing the charged particle to move in the circular path. So if we say that magnetic force provides centripetal force to the charged particle. Okay. So magnetic force has a formula FB BQV, right? And centripetal force is a formula FC equals mv square over r, right? Then we can say that FB is the only force acting, so mv square over r, okay? And in place of FB, we can write this value. So BQV is equals to MV square over R. So Q and Q goes off. BQ is equals to MV over R, right? This is the this is some of the derivation. Now they're saying they want us to introduce the voltage, right? So we have to remove the velocity and introduce the voltage, which for which we have to use this equation, right? So using that, um, okay, so BQR over M is basically V, right? And previously we derived that V is equals to under root 2 2VQ over M over M. Okay, so instead of that, I can write this one, right? And Hmm. Yes. So now after equating the two thing and removing the root, it become B square Q square R square over M squared is equals to 2VQ over M, right? So M N squared goes off, Q N squared goes off, and we want the specific charge to mass ratio. So Q over M is required, okay? So leave the Q and M here and bring everything to the other side. So 2 capital V, the voltage, divided by P square and R square, right? Yes, fine, proved. Okay, is that clear? Fine. Okay, please move on. So they are saying the electrons are accelerated through the potential difference of 230. The electrons are injected normally, which means perpendicularly into the magnetic field of the flux density 0.38 millitesla. The radius of the circular orbit is this much. Use the information to find the specific charge to mass ratio. So we have Q over M as the specific charge to mass ratio. Okay, Q over M is needed to be found, and 2V over B square R square. So 2V over B squared and R squared, right? So just put in the value and solve. So 230, right, divided by 0.38 exponent negative 3 and whole squared, right? And you have 14 exponent negative 2 and whole squared, right? If you solve, you will get, okay, so you'll get 8.1313 exponent 10, okay? Since most of the thing in 2SF, so 8.1 would be a good option, right? So, so this is the answer. Oops, wait. I didn't do that multiply by 2. Yep, sorry. It should be times by 2, and then you will get 1.6 exponent 11. Fine. They're saying suggest why the arrangement outlined in second part using the same value B and V is not practical for the determination of the specific charge to mass ratio of the alpha particle. Okay. Um, So if we try to figure out what would be the charge to mass ratio of alpha particle, so charge is 2 times 1.6 exponent negative 19, right? And mass is 4 times 1.67, 1.66 exponent negative 27. Okay. So the charge to mass ratio is very large. Okay. Mm, Q upon M, yes. So the charge to mass ratio I'm getting is very large, which means it will give this very small radius. And because if this is the 14 centimeter radius, and for that we're using this much 0.38 millitesla as a magnetic field, and yes. So if this value goes larger, which is I'm getting as 48 or 4.8 exponent 6, so this value would be very small to measure, right? So maybe this could be the option, but much smaller. Charge to mass ratio. Okay, so I can say that um, the charge to mass ratio of alpha particle is very large. Okay, but it is not that much large because the charge to mass ratio over here is exponent 11, and I'm getting the charge to mass ratio as exponent 6. So which means like half the value. So it will still be measurable. Mm, mm, mm. No, there should be some other answer or some other calculation that I'm missing. Okay, so mass would be higher, higher, and higher. If you do alpha particle, the charge to mass ratio of alpha particles is 2 into 1.6 exponent negative 19, right? And 4 into 1.66 exponent negative 27, right? So you will get 4.8, okay? 4.8 exponent 7, 4.8 exponent 7, okay? So it has a difference of at least 1,000 or maybe 10,000, right? The difference between the specific charge to mass, the specific charge for the electron and for the, okay, use this to calculate the specific charge of an electron, charge, specific charge, okay, specific charge. If we work out for the specific charge directly by its value, so charge of the electron is 1.6 exponent negative 19 and divided by 9.11 exponent negative 31. So, yep, it is approximately 1.75 exponent 6. And the charge to mass ratio of alpha particle should be smaller than that because in the denominator we have the larger value than that one. So it will give me the smaller answer. So charge to mass ratio of the alpha particle should be smaller. Okay, okay, fine, 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 got it. Basically, what I got as 48.4.8 exponent 7, right, as my charge to mass ratio for alpha particle, right? So comparing that with the previously calculated value, So this value is quite small, right? So if you have this value smaller, then the radius would ultimately get larger, right? And if the radius would be larger, then it would be like difficult for you to have this type of circular paths, right? Or it would be impossible for the alpha particle to complete the circular motion. It will maybe hit somewhere outside, right? So we can say that the charge or the specific charge, the specific charge of an alpha particle is very small. Okay, so it required large distance or large radius. Okay, so this could be the problem, right? Okay, do you understand? Now, so another question. Okay, skip the Tesla. So they're saying a stiff metal wire is used to form the rectangular frame, measuring this and that. The frame is an open at the top and suspended from the sensitive Newton meter, right? Okay, there's a current and fine. Okay, the open end of the frame are connected to the power supply so that there's a current in of the 5 ampere. Okay, the frame slowly lowered into the magnetic field of the flux density B so that all sides of the um this is something, no, you can ignore this one because we didn't study that yet. Okay, try this one. So they're saying that we have the sphere of a mass, okay, and the charge this much. The sphere is in the uniform electric field that act vertically upward as shown. Fine. Sphere, okay, fine. Force exerted on the sphere by the electric field causes the sphere to remain at the fixed stationary height. Okay, fine. So basically, the gravitational force and the electric force may be equal and opposite, so that's why. Okay, there is a uniform magnetic force in the region of the magnetic field. In the region of the electric field, the sphere move at the speed of this in the horizontal plane. The magnetic field causes the sphere to move in the circular path of the radius this much, and blah blah blah. Fine. They are saying determine the direction of the magnetic field. Okay, so it is coming out of the plane, right? The charge particle, the force is right here. Okay, so basically. And the charged particle is moving that way. What direction? Okay, fine. So the charged particle is moving that way, right? Okay. And with its position, the field or the force is in this direction, right? So we have the positively charged nucleus, right? So if you align the Coulomb Fleming's left hand rule, so it would just be your second finger is in this direction, your thumb would be in that direction. Okay, so I'm getting into the plane field, right? Into the plane field, right? So your second finger should be in this direction, okay, and your first finger should be in that thumb should be in that direction. So your first finger would be into the plane, right? So that would be into the plane, into the plane, right? Okay. Explain why the motion of the sphere is a horizontal circular path. You can say that the magnetic force, magnetic force provides centripetal force to the charged particle Okay, and you have to mention that they're perpendicular to the field, right? Otherwise, it won't be in the exact circular motion, right? So yes, okay. The field and the velocity, the magnetic field, the magnetic field and the velocity are perpendicular to each other, right? This is important thing, okay? Perpendicular to each other, okay? Then they're saying uniform electric field strength. You have to find out. So E is equals to F over Q, okay, or V over D, okay? Or do we have any other thing? Okay, so we have given us with the mass and the charge, okay? So do we have the acceleration or some sort of thing? We have the radius. We have the velocity? We have the velocity as well. Okay. So okay. So E times Q is equals to F. Okay, and this F will provide you with a um. Okay, fine. Because um electric field and electric force, this is the direction of the weight, okay, okay, and this is the direction of the electric force, Fe, right? So we can say that wait, in electric field, in electric field the weight is equal to the weight is equals to electric force, okay. So you can now say Fe Fe is equals to weight, okay, and E times Q is equals to mg then, and then um, mass is 1.6 exponent 10, 1.6 exponent negative 10, okay, into 9.81 divided by charge is given as 0.27 nanocoulomb, right? 0.27 nanocoulomb, 0.27 nanocoulomb, right? So you can calculate. And we are getting 5.81, okay. By considering the magnetic field on the sphere, show that the flux density of the uniform magnetic field is 0.15 Tesla. Okay. If we say that the magnetic force provides centripetal force uh, to the charged particles, so we can say that FB is equals to BQB and FC is equals to MV square over R, right? And applying those, FB is equals to mv square over r, right? Then bqv is equals to mv square over r, right? and we are interested in finding B. So the rest of the things would be mass of the charged particle was 1.6 exponent negative 10. Okay, and velocity of the charged particle is given as 0.37. Okay, 0.78 basically. 0.78. Okay, divided by the Q has the value of 0.27 exponent negative 10 negative 9, and the last one is going to be um Q, and R is 3.4, I think 3.4. Okay. Okay, so now you can calculate. So I'm getting the B as 0.1359, so that would be rounded off to 0.14, right? So Tesla. Now that is completed, and wait, can we try that one? No. Semiconductor hole probe. Wait, I can we can do two question. One, I think this one, or maybe that's the easy question. One would be that one, and electric field and magnetic field. So we can do this one because of, and it should be the velocity selection question. The travel, okay. Draw beyond the plates, region of the electric field, direction of the uniform. Okay. Okay, just note this one. Let's try this first, and then okay, last two question. So we can ignore this. Okay, so the electrons are moving. Okay, we've mentioned a lot of things. Okay, set the direction of the magnetic field. Okay, so you have the electron, which is the negatively charged particle, right? Negative charged particle, which is moving in this direction, right? In this direction, right? So you have to place your second finger that shows the direction of current in the opposite direction to the positive charged particle. Okay, and I'm getting it downward, right? So it is downward. The magnetic field is downward into the plane. Okay, into the plane, right? Because your second finger should be in this direction, opposite to the direction of motion. Your thumb should be in that direction. Okay, and doing that, your first finger will be into the page, right? Okay, so moving on. Show that the magnitude of the force exerted on each electron where the magnetic field is this much. Okay, so they have given us the speed, the magnetic flux density, and everything. Okay, so FB is equals to BQV. Okay, since it is entering perpendicularly, so we don't have to put sine theta component, and 0.48 4.8 exponent negative 3. Okay, 4.8 exponent negative 3, right? The value of the charge is for the electron is going to be 1.6 exponent negative 19, and for the velocity it is going to be 1.7 exponent 7. Okay, right? Okay, so that gives me 4.8 exponent negative 3 into 1.6 exponent negative 19 into 1.7 exponent 7. Okay, so I'm getting 1.3 exponent 14. Okay, right? Now, in the next question, they're saying, on the figure 6.1, draw an arrow to centripetal force where magnetic field point X. Okay, so at point X, the centripetal force should be toward the center of the circle, right? This is basically our FC, right? The centripetal force. Okay, and use the information to calculate the distance between the path of the electron entering and okay, basically they're asking for the diameter, right? So you can say that um, FB is equals to MB square over R, okay, and then F B QV is equals to MB square over R, okay, and R is going to be so the mass of the electron would be 9.11 exponent negative 31, okay, times the velocity, which is okay 1.7, okay, and B is supposed to be 4.8 exponent 3 negative 3 negative 3, right? And Q is 1.6 exponent negative 19, okay? That will give me the radius. When I times by 2 everything, I'll get the diameter, okay? So 9.11 exponent negative 31 into 1.7 exponent 7 divided by, okay, multiply by 2. I'm getting 0.04, okay? 0.020, okay? And yeah, times it by 2. So for diameter, it should be 2 times 0.020. So that gives me 0.040, right? Which is 40 centimeters, right? Now, they're saying the electron replaced with the positron that are moving with this speed. The speed is greater than that along the same initial path as shown. The positron enter magnetic field. Okay, okay. So positron has a positive charge, so it will bend upward. Okay, and it has double the speed. Okay, so doubling the speed will causes the magnetic field or magnetic force to be greater. So it will cover the greater circular path. Okay, right. Okay. So basically, this would be the path of the proton, positron, okay? Path of positron, okay? And yep, that's it. Okay, that's it. I'm not doing the last question. That's it. Chale. Bas. Okay, I've sent you the question, guys, by the way. So just try those, and I'll share you the note as well. So please try them, okay? Chale. Okay, take care. Lafes.
Professor.
Lafes.